எத்தனை பேர் இருக்காங்க?
7 பேர் வராங்க.
ஆயிடுச்சுல. என்ன கூட கனெக்ஷன் நான் ஃபர்ஸ்ட் பேசுறேன். என்னாச்சு? இல்லவா ஆரம்பிச்சு நான் இருக்கிறேன். நான் ஃபர்ஸ்ட் பேசுறேன். ஆரம்பிச்சு சாரி சார். எவ்வளோ ஆயிடுச்சு? 77. அது ஒரு 14, 77, 91, அது ஒரு 98. நீ கூட அவருக்கு இவனு கொடு. வில்லுன்னு அதை ஆரம்பிச்சிருப்பான். நீ கூட அது வந்துருவான் நம்மளுக்கு. வி 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 எல்லாம் ஒன்னா எடுக்கிறாங்க.
Hello.
Sir,
shall we, sir?
Sure. Yeah,
Hello, sir. Can you hear me, sir?
Yeah, we are able to hear you.
Yes, sir.
Please, go ahead. சார் கொஞ்சம் கீழே இருக்கு கேமராவை. குட் மார்னிங் சார். கேமரா கேமரா. குட் மார்னிங் சார். Good afternoon, sir.
Congratulations for your hard work.
Yes. Start coming.
Shall I start, sir?
Sure.
Sure. Good afternoon to everybody. Good afternoon to everybody. As a patron of the webinar session, I invite you for the afternoon session of webinar on structure and formation of condensed matter or Raj Kumar, presently working at Kaudas Polytechnic University, France, for the postdoctoral research work. Also, it is my privilege to introduce Dr. Siva Surendra and Dr. Raj Kumar, our senior student of Physics Department of Physics Department, Uchalangobra College. Dr. Siva Surendra, presently working at Germany.
2017 to 2018, he is again a postdoc fellow in INSAT Allows, France, from where he is working again. His field of research interest is synthesis of nanoparticles by co-precipitation route, polyol process, and organometallic pathways and preparation of bulk oxide glasses. He is very good in handling the instruments like microfluid, stop-to-flow technique, flow setup for long reaction kinetics, and he is very good in all kinds of X-ray scattering experiments like small angle, wide angle, extended ray absorption, and he is very good in TEM, handling the TEM, UV spectrophotometer, PL, Raman scattering experiment, and all kinds of TGA analysis. He is also good in softwares like EXEFX, SAXS, WAXS, they are related to X-ray diffraction and all, Python program, Python and LaTeX. He received so many awards. To quote, again, like the morning's resource person, he also won the first award for his presentation on recent trends in physics held at C. Abdul Hakim College, Vellore, in the year 2005. He was doing third year BSc in our college at that time, and he also won best performer for oral presentation out of 25 speakers in the state level seminar on solid state physics held at Vadodara, Gujarat, India. And he is a recipient of Hero Talents Fellow for the period of 2016 to 2017. He has also worked with so many synchrotron facilities in France and in Switzerland. He co-supervised 4 summer projects for their master thesis. He has organized awareness workshop on UGC DAE CSR facility held at University of Hyderabad in the year 2013. To his credit, he has published more than 16 papers in the international journals which have with a high impact factor, and he has presented some invited talks in I will read out some selected conferences. He gave an invited talk on tuning the morphology of cobalt nanoparticle synthesis condition in an international conference on polyol mediated synthesis in the year 2018, Madrid, Spain. He also made an oral presentation on urethane gold nanowires, growth mechanism and self-assembly gold 2018 in Paris, France. He has also presented on the topic of understanding ions to crystal transformation via intermediate state. The conference held on novel material engineering and properties, synchrotron solid, Paris, France. He has presented a poster there, and he has also presented a poster in the 59th DAE Solid State Physics Symposium held at VIT University, Vellore in the year 2014, and he has given an invited talk on invariant bandwidth of erbium in Zetono PBO telluride glasses, local probe bar model in the 58th DAE Solid State Physics Symposium in the year 2013, Thapar University, Patiala, India. So with all his credits, he is going to deliver a nice topic to you, and on behalf of the faculty, students of PG and Research Department of Physics, and on my personal behalf and on the behalf of Professor S. Marimuthu, Principal in charge of our college, happen to be the teacher for both these resource persons. We are lucky to have them in our college, and I take this opportunity to thank Rajkumar for readily accepting this our request, and he is now going to present his topic of research interest from France. Now I take leave and I hand over the session to Dr. Rajkumar Ramamurthy. Thank you. I hope you all will enjoy. Friends, we had a very nice session in the morning. I hope to continue the same. There was no interruption in the morning session. Likely in the afternoon session also, I request all the participants to mute the mic as well as the screen. Then if at all you have any doubt, please type your doubt in the chat. At the end of the session, I believe the resource person will be ready to answer your question. Rajkumar Ramamurthy is now presenting. Thank you. Thank you, Rajkumar. Please.
Thank you, sir. So are you able to see my presentation, sir?
Sure. You are yet to you present it in the two webs. Two tabs.
Yes, I have.
Yeah. One is okay.
Okay.
Second is also okay. You can go.
Okay, sir. So good afternoon, all. Thanks for joining this presentation. So myself, Rajkumar Ramamurthy. I'm working as a postdoc at ENP Toulouse, France. Today, I'm going to present the topic structure and formation of condensed matter. Through this presentation, I would like to share some of ideas and concepts of condensed matter to you all. So basically, I'm working here. Toulouse is down south of France, which is situated here. So along with many national laboratories and research institutes, there are other interesting places of energy. Then what kind of structures can exist in these matters? And finally, I end my presentation with few examples of the formation of condensed matter. So what is matter? Matter is any substance that has mass in its own rest frame and take up some space by having volume. So which means if a substance should be a matter, then it should have a mass as well, it should take some volume. So in our daily life, we could see three different states of matter. One is solid, the other one is a liquid, the other one is a gas. So for these three states, the basic building blocks are either atoms or molecules. But the matters are not limited to these three states. There are other states of matters are existing and are predicted by several peoples. So out of them, I present just two here. So in Earth's conditions, you would witness a few other matters like plasma, where when during the lightning, the plasma has ionized atoms, electrons, and atom itself. Whereas in another harsh condition by cooling a system to a temperature close to 0 Kelvin, we end up having a Bose-Einstein condensate. So this is a matter proposed by Satyendranath Bose and Albert Einstein. So there are few evidences exist to support the formation of Bose-Einstein condensate. So with this, so why do we have these different states in common life, like a solid, liquid, and gases? How they differ? So basically, the solids are rigid material. They have a shape, and the rigidness is coming from through this three different kind of bonds, either a covalent bond, ionic, or metallic bonds. Whereas liquid are free flowing, but it takes a volume of a container where we put, and the intermolecular forces are driven by hydrogen bonding. Whereas in gas, we see a weak van der Waals bonds, which is a free flowing again. But in ideal gas condition, we should not see any kind of intermolecular forces. So basically, we witness these three different kind of matters because of different intermolecular forces and the different interkinetic energy of the systems. So we understood that the matters why we see the states why we see differently is because of the different intermolecular forces and kinetic energy. So let us see how the matter can be presented in the energy scale. Let us take a solid. In the morning, Siva might have presented the formation of matter like a condensed phase. So we know from the presentation that the condensate phase is a ordered, typically condensate phase is a ordered one. So let us say solid. So if we supply some energy, so heat, nothing but a heat. So if we supply some heat, what happens is the solid transforms to liquid, which means what we are doing is, so we are trying to break the bonds and we are giving a more energy, which means we are giving a energy to move randomly inside the system. If we supply further energy, what happens is the all kind of intermolecular forces breaks and it moves very randomly inside the container. If we supply further energy, we end up with ionized states of atom. So which means we have most are ions plus free electrons and few unionized atoms. Whereas if we go in the other direction from gas to the other direction by cooling, then we end up with Bose condensate. Bose-Einstein condensate is nothing but it's a overlapping of several atoms at a one single particular energy level. So we see this Bose-Einstein condensate by example in the following slides. So with this, you are aware that any kind of matter can be achieved from one to another by supplying heat or by sucking some heat from the system. So we understood that matter can be transformed from one stage to another. So with this, we have some questions, fundamental questions. So what kind of forces exist and what kind of forces can position atoms in a given system? In solids, we have a rigid atoms at a given position, whereas in liquids, we have a free-flowing atoms, whereas in gases, there is no forces at all, and it is randomly moving. There is no interconnections. So why we need to understand the structure? Because the arrangement of atoms guides the properties of matter, either physical properties or magnetic properties or optical properties or electrical properties. This structure of states are very important. So we would like to understand why we have a different structures of matter and how it differs from one from another. So with this, I present few examples of X-ray diffraction of different states. So before going to the results, I present here briefly what is X-rays gives out when it passes through the states of different matter, states of matter. So let us say, so we have X-rays and we pass through one of the states in a transmission mode. So in typical diffraction or X-ray scattering, what we observe in the lab is a reflection mode. What I present here is a transmission mode. So we are passing X-rays into a substance. And once the X-rays interacts with the substance, then it scatters. So what we see at the end in the CCD is nothing but an image plate, which records what is happening between the X-rays and the substance. So we record the patterns at the screen. So what happens here when X-rays incident on the substance? What happens really? So what X-ray sees inside the substance? So this is a question. So the thing is, so we know from as like in Newton equations of motion. So we know when a body is at rest or continuous motion, it remains like that. It won't change it until we exert some forces externally. So similarly, here also, the atoms is surrounded by electrons. So these electrons moves around the nuclei. So once we send a X-ray is nothing but an electromagnetic signal. So these electrons are disturbed. So once this disturbed electrons, what it does is it emits X-rays in all directions. So what we see is the interaction of X-rays with the electrons, not with the nucleus in the atom, just the electrons. So this electrons interaction will give us X-rays. So each atom scatters some X-rays. Then this each atoms, how it scatters, and depending on the position, it can be correlated. So as a result, we end up with some kind of correlation, and we could understand how the atoms are arranged in the system. From that, we can propose the structure of a given system. So with this introduction of X-rays, I move on to the results. So typically, solids are classified into two states. One is crystal, another is amorphous. Crystal, as you know, it's a periodic one. So once we shine X-rays on the crystals, because of the periodicity, there is a strong correlation between one and another atoms. Because of this result, we will see a diffraction pattern on the scattering screen. So as a result, we see some spots. So what we see most of the time is the end result of the diffraction spot. So like shown here, we have some peaks. So it is nothing but a end of this end calculation of the diffraction spots. Whereas in amorphous, so this we all know about the crystals. So the Bragg's law can tell us what is the crystal structures and what is the condition for the diffraction peaks and other stuff. Whereas in amorphous, unlike the crystals, we don't see a diffraction spots. We see a diffuse rings, which leads to what we have, a broad hump of two peaks here for this example. So with these two broad peaks, we will not conclude any kind of things from this pattern. So how the structures is arranged in the amorphous, and how the atoms are placed, what are the kind of atoms, we don't know at all. So this is the typical X-ray diffractions of crystals and amorphous. Now going on to the liquids. So this is a example of a liquid scattering. So where here we doesn't see the diffuse scattering at all. We just have some scattering, random scattering on the screen. If we integrate this, we end up with this diffraction patterns. So again, we are clueless with the structure what we have in the liquid state. So to understand the structure either in the amorphous or liquid state, we need a support. The support is called a simulation. So we need a simulation, which is a theoretical model. So what we do is we select a box. So we put some atoms, what we are investigating through the experimental way. So we put the atoms, but the simulation box is limited. So here we take around a few nanometer or angstrom volume, angstrom volume. So then we simulate the atoms inside the simulation box. Then with the help of, if we are doing a molecular dynamic simulation with the help of Newton's motion equations of motion, we can follow the trajectory of the atoms or molecules inside the systems. With the help, we can restore the position of atoms, and from that we can understand the correlation what they have in the system. So from this we understood that we from crystals we can easily derive the structures, whereas for amorphous and for liquids it is difficult to get the structure very directly. So for that we need a simulations. So with this I finish the structures of a condensed matter. Now I pass on to the formation of condensed matter. So basically I present the following results from the fluid states, either a gas or from the liquids. So basically the formation of condensed matter from liquid states can be described by classical nucleation theory. So what it can tell us is, so we have some solution. So what we do is, so once we reaches a supersaturation concentration, which is nothing but a more than the number of atoms or molecules in a given solvent. If we exceeds more than the number of levels, we call this as supersaturation. So once we dissolve more and more atoms and molecules in the system, so the volume of the free energy of these atoms is no more stable in the given solution. So it tends to form a solid substance. So by the following way, so there is when we have a supersaturation concentration in the system, there is a two kind of energy comes into the play. One is a surface energy, another one is a volume free energy. So the surface energy is nothing but energy which is compensated for a given number of bondings, or we can say there is a interfacial layer between the solid newly formed phase and the solvent itself. Whereas the volume free energy is the free energy of a given state in the given system. So once we passes the supersaturation concentration, the two different energy interacts and it fights. So once we start to form atoms by the thermal fluctuations in the system, then because of surface energy, these atoms tends to go out because we have a higher energy configuration at the surface. For example, if we have a 12 coordination with the gold atoms, but at the surface we will have only 5 or 6. So because of the highest surface energy on the system, so we tend to lose the substance. So this computation goes on. Once it crosses the activation barrier by attaching atom by atom, and it reaches a nuclei. So this nuclei is nothing but a system which passes the activation barrier, and itself contains the crystalline structure information of the final states. So once it crosses the activation barrier, it's like a uphill. So once we reach the uphill, the downfall is very smooth. So we end up with final nanoparticles. So basically, the classical nucleation theory, what it describes is, so to form a system, either to form a system, the system should be atom by atom attachments, and the nuclei itself contains the crystalline structure of the system. So with this, I go on. There is a problem. Just a moment. I have a problem. I cannot move the slide. Yeah. So first example is the hailstone. So hailstone is nothing but it's ice crystals coming from the sky. So it's coming from the sky. Yes. From where? It's from clouds. So what are clouds? Clouds is nothing but it's a substance which has a tiny water droplets in it. So for the audience, there are plenty of clouds are there. There are 10 different clouds are there. So one of the clouds give us this hailstones. So how the hailstones forms? So I present here by some video. So first for this, we need to have a thunderstorm cloud. Then the surface of the cloud should be at a very freezing temperature, and the bottom cloud should be lower temperature. Then we need an updraft of wind. So what it does is it takes a water droplets from the bottom of the clouds to the top clouds where the temperature is very, very low. So by doing this, the thermal equilibrium shifts here. So once it reaches the temperature below the 0 degrees Celsius, it turns into a ice, and the ice formation is grows, and it reaches a bigger size. Once it reaches a bigger and heavy size, it drops out. So this is why we see a hailstone and in a different condition. So the thing is, we need to have a hailstone, we need to have a thunderstorm cloud. Not all the clouds, just the thunderstorm clouds. So in the another example, so this is somewhere, this is a frozen lake. Let's see what it comes out from the frozen lake. So someone is coming here, and he is trying to break this frozen lake, and he has some fire. He is trying to break it. Oh, there is a fire. So you all people are wondering, right? So how a fire comes out from the ice? So still the fire is there, but we are not able to see it. So you see, we can see some boiling water. Yes, there is some fire. Yes, it's continuous. Yes, it goes on. So it's coming from ice. So how a fire can form from ice? It should not be, right? Yes, this is the case here. So what we see here is it's not definitely a ice. It's something else. So what it is? It is nothing but the gas hydrates. So what is gas hydrates and how it is different from ice? Let's see that. So how it's different. So let us first see how ice forms. So as we all know, 0 degrees Celsius is the freezing point if we come from higher temperature, whereas the 0 degrees Celsius is the melting point if it comes from low temperature. So once we crosses this 0 degrees Celsius, either we freeze into a ice or either we melt ice into a water. So to get water, to get ice, so we have to cool from a higher temperature to lower temperature. So once we crosses the freezing point, we nucleates as proposed by classical nucleation theory. We are far from equilibrium, thermodynamical equilibrium. So we end up with some nuclei, and then we can go to the 0 degrees Celsius. That leads to that is nothing but a freezing point. We end up with crystals. So at the end of a reaction, we convert all water into a crystals. So the freezing point is nothing but a thermodynamic equilibrium line which separates out the water and the ice. So if we do the same to the gas hydrates, will it form? No, because we don't know yet what is the condition for the gas hydrate formation. So now we have seen how a ice forms and why, and for the same condition, we are not seeing the gas hydrates formation. So how the structure of the ice looks? So it's hexagonal in structure, whereas the gas hydrates is either it takes a cubic or hexagonal structures. So gas hydrates are nothing but some molecules, smaller molecules, either methane or cyclopentane or something else. It's organic molecules trapped inside the water cages. So this is called gas hydrates. So depending on the size of the molecules, organic molecules, we end up with the different crystal structures and different kind of arrangements in the gas hydrates. So how the gas hydrates forms? So will it follow the classical nucleation theory? Not yet. They are not aware of this kind of formation. So the possible proposition for the gas hydrates is, so we have a solid, we have a liquid water, and then we have a gas phase. So once the liquid water freezes out, there might be some interface between this ice, frozen ice, and the gas phase, nothing but some small molecules. In between these two, there might be a thin layer of liquid water exist. So during the cooling, further cooling, we may end up with some kind of water structure organization in the liquid phase that leads to a cages. And these cages, further, if we cool and cool, then the gas molecules or the small molecules, organic molecules, enter into the cages, and which leads to form a gas hydrates phase. But what we know from the classical nucleation theory is to form a final nanoparticles or a final crystal states, we need to have a atom by atom built, and the nuclei should have already possessed the final crystalline structure of the phase. In this case, we are not able to achieve the atom by atom. As well, the nuclei itself is not a crystalline structure phase. So we need to have a cages, first the water cages, and the gas molecules go inside the water cages, and then it forms. And this cages is already a crystalline structure? Not yet. Not yet. They are unstable and amorphous phase. Whereas in another proposition, so what happens is this dissolved gas phase in the water, it tries to interact randomly, and itself already it has in a molecule state. It's not by atom, it's by molecule state. The organic is already attached with the water molecules, and these attached molecules arrange randomly. It's not atom by atom. It's arranged randomly and it forms a amorphous intermediate phase. Again, it is deviating from the classical nucleation theory concept. And then we end up with a gas hydrate phase. So here, the formation is neither atom by atom attachment nor the nuclei as a crystalline structures. So now I go on to the Bose-Einstein condensate state. So before going to Bose-Einstein condensate state, so what is temperature? Let us see from this thing, what is temperature? So we have some energy levels for a given atoms. This is a free flowing gas molecules, it's moving. So what we are doing is it is having some energy levels. The black dots here is the energy level of atoms, which is wandering inside the container. If we cool down this, so what happens is the energy of atoms is getting dropped and it is coming to the lower energy levels by. So at the simultaneously, what we are seeing is the atoms volume is spreaded. So you see it keeps on moving if we decrease the temperature. So it's going. We are continuously decreasing the energy. So you see, so all the black dots are coming to the lower levels. Yes. So where is the minimum level of the atoms? So that time what happens is all the atoms comes to the energy level of minimum. That time the atoms tend to spreads and it occupies all the volume. So I play it again. Let us see what happens again. So again, the gas atoms are moving inside. So it has specific energy. So you see all the moving atoms is not having the same energy. It has different energy states. So it's moving on. So we are trying to decrease the temperature. You see the temperature bar is decreasing here. So it's slowly decreasing the temperature. So that time the atom motion is slowed down. Simultaneously, the atom's volume spreads out. So it spreads out. So once it reaches minimum energy, so all the atoms overlaps together. This we call as a quantum entanglement. So it's nothing but all the atoms loses their individual identity and it forms all the atoms together. So what we know from this is so temperature is nothing but a parameter which measures the internal energy of the system. So what we know is the temperature is something which turns on the internal energy of system or modifies the internal energy of system. So and further, what we know from this video is whenever we have a system, all the atoms or molecules in the system may not have the same energy. It has a energy population in the system. So we know from the de Broglie equations that once the atom has some velocity, it has some wave nature. So if you cool down and if you supply the atomic mass in the de Broglie equation, we end up with a large spreaded wave for a given atom. As a result, we have a widespread of atoms which lost its individual energy, and we end up with quantum entanglement. So how can we cool the atoms? So we have a system, gas systems. How can we cool this? So for this, people have done some experiment. So here what I'm going to show you is the video which expresses how free moving gas atoms can be cooled down to a certain temperature such that we can form a Bose-Einstein condensate. So here the people have used a laser as a cooling tool. So you might surprise, why laser? Laser we know as a heating substance, but it's not a heating wave. It's a one we use to cool the substance. So what it means? So from the previous slide, what we are aware is, so if we stop the movement of atoms or we slow down the movement of atoms, the temperature of the system drops. So which means what we are doing is we are reducing the internal energy of system by cooling down the temperature of the system, or we are reducing the internal energy by applying a force against the movement of the atoms. So by that way, we are stopping or slowing down the atoms. As a result, the temperature of the system goes down. So similarly, the experiment, what I'm going to show here is demonstrate the same. So what here is, so we have some kind of atoms, the electrons or the LO1, it's moving. So here, this is the experimental one. So here, the violet moving one is the atoms, gas in a gas state. So we are hitting the atoms by laser pulse at a given frequency. So as a result, we have a cooling down of the temperature. Then we are applying a magnetic field. What we are doing is we are removing some hot atoms, and as a result, the atoms is entangles and it loses all its individuality, and we end up with a single state. You see the video, the final temperature shows it's a 177 nanokelvin, which is very, very close to the 0 Kelvin. So again, I play this. So let's see what happens again. So we have atoms. So the electrons are moving around it, around the nucleus. Then there is an experimental chamber where the atoms are moving. Then we are hitting the atoms by using a laser at a particular frequency. Then we are slowing down the motion of the atom. As a result, we see a drop in temperature. Then you see there are some atoms going on here and there. Then we have a quantum entangle effect as a result of cooling down the system to low temperature by using a laser as well with the help of a magnetic field. So again, once again, I'm playing this video. So we have atoms. So the nuclei is surrounded by electrons, it's moving. So we are going to hit this atom in an opposite direction to slow down it at a given frequency. So we are hitting it. So what we are doing is we are stopping the atoms. Then as a result, we are decreasing to a millikelvin, which is not sufficient. So what we are doing is we are applying a magnetic field. So what we do is we expel the red atoms from the system. So here we see a quantum entanglement effect again, and it is because of the cool down of temperature to nanokelvin. So once again, I play this video finally for final time. So we have atoms. Then we are hit by the laser in opposite direction. Then the atom's motion is slowed down by the frequency of the laser. So this is a millikelvin. It is not sufficient to form a Bose-Einstein condensate. We are applying a magnetic field and removing the red atoms. The red atoms are nothing but hot atoms. Then we are cooling down. As a result of reaching the lower temperature, we have a quantum entanglement effect. And as a result, we lose all the individuality of atoms and we have a single state. So this is Bose-Einstein condensate. So we know from this, laser can also be used for cooling the substance. So here we understood that if we stop or slow down the movement of atoms, the temperature of system automatically drops down, and which may lead to another state. So with this, I finished the presentation. So we know from the things from the previous slides that we reasonable understanding on the solid state structures of crystals, whereas we are lacking still the understanding on the amorphous and liquid states. So we need simulation help to understand what kind of arrangements is present in the amorphous and liquid state. So as before, there is a strong effort is needed to understand the formation of matter in the nature, like a hailstone or gas hydrates existing in the nature. And we know from the gas hydrate phase, the available theory is not enough to support the formation. So we may need new theories to build up to understand the formation of condensed matter. And finally, the states of matter, what we know is not limited. There are other plenty of states of matters are there, and it's predicted. So there are some possibilities are there to find some more. So with this, thank you.
Okay. Thank you, Dr. Rajkumar.
Yes, sir.
Hello.
Yes, sir. Yes, sir. I'm hearing.
Yeah. Thank you. We'll go ahead with some questions and take some time questions for now. Just
Yes,
a
sir.
reminder. Please be sure to type your questions into the chat box. We are here to convey your doubts to Dr. Rajkumar Ramurthy. The very first question is a very simple question.
Yes, sir.
Why we are mentioning in XRD 2 theta instead of theta?
Mm-hmm.
In XRD,
So it's because of the angle of incidence and angle of reflection.
Yes.
So if we draw an angle between the incident ray and the recorded ray, it's 2 theta. That's why we take it as 2 theta.
Right. Is there any other questions from the participants? You can type your doubts in the chat box.
Hello.
Yeah.
Yeah, Javina ma'am.
Yeah, sir.
Good afternoon. Keep going.
Sir, I have one basic doubt.
Yes, ma'am.
Actually, what is the difference between crystallite size and grain size, sir?
Yeah, they are both are same.
Yeah.
Because somebody reporting in STEM studies, it is grain. We are observed the grain. And what we are calculating from XRD results, it is crystallite. Actually, what is the exact difference between crystallite and grain?
It's a different notation, ma'am. Actually, people report in different forms. One is domain size, grain size, crystallite size, coherence length. It's terms of different names. Otherwise, it's more or less it's the same.
Both are same. But when we are calculating the crystallite from XRD, it is totally different from the size observed from the SEM image, no, sir?
Yes. So I hope you might have subtracted. So are you talking from the real experience or from the manuscripts or from articles?
No, real experience.
Okay, ma'am. So whenever you are calculating a crystal size from the diffraction, are you considering the instrumental correction?
No, we are not considering.
So this might be the reason, ma'am. So what people generally do is they do a diffraction for a standard sample like a lanthanum borate or silica. First, they estimate the width of the instrument broadening. Then they use this instrumental width broadening in the unknown compounds. Then they subtract this instrumental width contribution. As a result, they will get a right length, that is coherence length or a domain or something.
Okay. Thank you, sir.
Thank you, ma'am.
Yes, ma'am.
Thank you, sir.
Thank you. Now, we have from Mr. Sabrish Sibi, Dr. Raji, his question is, sir,
Yes,
when
sir.
the atom gets ionized on applying laser while cooling, I think he is about Bose-Einstein condensate.
Okay.
His question is, will the
Yes, sir.
atom get ionized on applying laser?
Ionized, yes, there will be a possibility is there, sir. Because whenever we talk about some process, for example, if we incident X-rays, the electrons might be knocked out. So as a result, we may see some electron process or some kind of transition from higher excitate to the lower excitate. So there are other possibilities also exist, but the most of the thing what we see in the Bose-Einstein condensate is by the atom itself, not by the ionized one. But the possibility of ionization is there, but not 100%, maybe 10% or few percent.
The demonstration was very nice. So they have a lot of questions on them. One
Okay.
Mr. Lokesh Kumar from our college, if I am correct, he just wanted to know the properties of hailstone.
Okay. What kind of properties he is expecting, sir?
No, just he made a just he typed like this only. What kind of
Okay.
properties? Yeah. You can mention one or two.
Yeah. So it's a similar like ice. There is nothing, but nothing different from ice, sir.
Okay. What type of bonding it is? Jay Bharati has asked this. Hailstone
So,
having which type of bonding it is? Is it a hydrogen bond like it?
yes, definitely it should have hydrogen bond, but the water molecules is bonded by the covalent bond by itself. But the water molecules interacting with another intra-water molecules is by hydrogen bond. Yes.
Okay. One Mr. Ramchandran Murugesan, his doubt is commonly the crystalline size is calculated from XRD peak using Scherer formula. Is it accurate?
Yes, if they include all the corrections, yes, it is correct. But we have to pay attention for all the correction, instrumental broadening, and if there is a stress is there or not, everything we have to consider.
Okay, one more question from Mr. Kumar. Please be on the line, ma'am. We'll be back to you. One Mr. Kumar, his question is, if laser is one of the factor for condensation, what is the temperature for laser surgeries? Is it varies accordingly?
Like I said, here in the Bose-Einstein condensation, we cannot use all kind of lasers. So we need to use a laser with a particular frequency, and we have to hit atoms in a particular direction. So these are the conditions. So if we are hitting atoms in a wrong direction, we are going to force the atoms to move faster. So we are going to increase the energy of the system instead of decreasing it.
I do have
So
a
we
doubt.
need to.
I do have a doubt, Raj. Here,
Yes.
you said see, reverse direction. I don't understand what you mean. The reverse direction heating.
It is like a simple, sir. If we, for example, if we ride in a bike, if a wind blows opposite to us, then our velocity is going to stop down, right?
Right. Opposition.
Yes. It's the same like here also, sir. If the atoms are moving in one direction, if we put a laser in opposite direction, then the atom is going to slow down. Otherwise, if we hit in another direction, the atom might get more kinetic energy and it moves fast.
Okay.
So in continuation to your system, the laser helps to cool down to millikelvin only, but that is not sufficient to form a Bose-Einstein condensate. To form a Bose-Einstein condensate, we need to apply additional magnetic field. So as we see in the PowerPoint, the red atoms get ejected out from the system. That is nothing but a hot atoms. So this hot atoms is expelled by the applying magnetic field. It's like we are helping while we are drinking a coffee. When we blow it, so we are helping to cool down the coffee, right? So that, the magnetic field also help to remove the hot atoms from the system.
See, where comes the entanglement here?
So for example, sir, if we apply let us take a system like a rubidium, it may have around 80 plus atomic mass. If we slow down, the velocity gets less, slower and slower. If we apply that in a de Broglie formula, so then we get around like 100 nanometer spread of a given atom. So what happens is when we cool down, the wave spreads out. So similarly, all the atoms in the system spreads out. So once it spreads out, so it entangled, right?
Okay.
It's no more in a specific 10 power minus 10 or some size.
They get
it's more than that.
Okay. There's one question. What is the nature of the glass transition between a fluid or regular solid and a glassy phase?
Can you say it again, sir?
What is the nature of the glass transition between a fluid or regular solid and a glassy phase? I think
so we cannot have a glass transition for regular solid. For example, all the amorphous material doesn't have a glass transition. The glass transition is a particular phenomena only exists in glassy medium, glass like a glass, or in the polymer material.
Okay. The next question is, there is a slightly jumping. Sir, what are the applications of BIC, Bose-Einstein condensate?
Yet to find their applications, sir. Still they are understanding the formation. So there are few evidences like in sodium, rubidium, they have done this, but they yet to find the applications.
One more question from Ramachandran Murugesan. I think it resembles Dr. Gabina Begum's question. What is the difference between crystalline size and particle size? So you have
particle size and crystal size, there is a difference because the particle might have many crystals in it, whereas the crystal size is just a crystal domain of the system. For example, if we have a 100 nanometer size particle, it may contain n number of crystals in it, but the crystal itself has one single domain.
The other question from Ravi Nove, morning also, he was very interested in asking question. Plasma state can create in Earth like in sun or star?
Plasma, yes, it's possible. Because for example, in sun we are at several thousands of Kelvin. So at such high temperature, definitely the plasma will be there.
There is one question from Subbalashmi of our college, if I am correct. She wanted to know the brief introduction for quantum entanglement. Once again, sir, she wanted a.
So what? Okay. So what? Maybe I can play the video again.
Right.
So for example, so what we are doing is, so here, so we have an energy scale of atoms moving inside the container. So it's moving, it's very fast. So all the atoms doesn't have a same energy level. It has a different energy states. So for example, you see now we are starting to slow down the motion of the system, which is nothing but we are reducing the temperature. So while reducing the temperature, the atom spreads out. You see, starting, yeah, now the spreading is more and more. It's widening as the temperature decreases, and the atoms also moving very slowly. So this, you see, it's already started entanglement. So one atom is already overlapping with another atoms because of the wave nature. Now all the atoms is more or less, so we cannot separate out which atom is there. So that's why I say when the temperature drops down to close to 0 degrees Kelvin, so we loses the individual entity of atom, then we spreads out and we entangle all the atoms in the system. That's why we call quantum entanglement.
Okay. The next question is, XRD is used to identify the formation of phases, but is there any technique through which it is possible to see the actual arrangement of atoms in the structure of condensed matter?
Yes, there are many techniques. XRD is there, but what kind of structure is interested in? For example, if you are specifically interested in the local structure, the extended X-ray absorption fine structure is used, where we can probe until the length of 10 angstrom level from the center of atoms what we probe. So the local structure can be understood from extended X-ray absorption fine structure, whereas the atom distributions can be understood by the total X-ray scattering also.
Okay. One Miss Malati Astro. Her doubt is, what is the role of condensed physics in astrophysics?
Astrophysics. So it's difficult to understand answer for me
right now. So what I will do is
Yeah.
I will give you your email ID to her. You please clarify afterwards.
Sure, sir.
One more doubt from Ritik Dhanush of our college. What is the advantages of quantum entanglement?
So there is no one is we are seeing another state of matter. That is where for curiosity mind this is very important thing. So we know in a common life we see only 3 different states of matter: solid, liquid, or gas. But we see a third another matter. So this is one, and so we can achieve this not in a regular condition. We need to go to a harsh conditions, like we have to use a laser, which is high energy system, and then we need to cool down to a nano Kelvin. So these are there is advantage. It's a advantage to understand more about this kind of matter, but not for the applications point of view at the moment.
Okay. I think probably he would have asked in the other way, what are the uses of quantum entanglement? Right.
Yes, could be.
It could be. Right now, again, Logesh Kumar has asked, sir, can you tell the size of hailstone?
Hailstone, it varies. Like what we see is like a few. Sometimes we see like in a few millimeters. Sometimes we can see in a few centimeters. So it varies, and it depends on the clouds. Like I mentioned, it depends on the top surface of the temperature, and how much water content in the lower surface. So it's all depends on the type of cloud, the thunderstorm clouds.
Okay. One more question from Ms. Murali Krishna Hari. Where does these BECs are used in everyday life? Bose-Einstein.
So at the moment, the applications are less or not found. So they are still understanding why it is happening and what are the real complication to understand. So these are the things are under process. So yet to know the applications.
One question, actually a doubt from my colleague Dr. Chidambara Kumar from Tirupati. Can you suggest some websites where we can find videos like you have shown to us?
So we can find. So the thing is, we have to search in a more accurate way, I would say. So the searching words are very important. So if you find the right searching word, I think you will find the right video.
All right. One more
either
question.
In the YouTube or in the Google itself.
Right. Thank you, Dr. Actually, I have one more question from one of my colleagues, Professor Jayanti. Hailstone, does hailstone have any medicinal values?
Yes, I heard this story about the medicinal value, but personally I don't know about this.
All right. Okay, we'll ask them to find out. One question from Dr. Vijayalakshmi. Hydrogen bonding is available not only in liquids but also in solids, because co-crystal is formed by hydrogen bonding. But you said it is in liquids only. What is your answer, sir?
So in some organic materials, the hydrogen bondings are there. So what Madam said is right. Some system. I am talking mostly the common solid materials. What I was talking is.
If the Santosh Kumar has asked if the applications are still not found, but why this Bose-Einstein condensation is so interesting?
Because the nature of state itself. So we form something at a very low temperature. The low temperature is not easily attainable in a normal day life. So we need to have a certain system. So this is the one thing. Second, the quantum entanglement effect. What happens? What happens? So if all atoms entangles, what kind of properties we can get, and whether this can be used for some other applications? Yes. These are the interesting thing.
Okay. I think there are no questions in our chat box. It means that there are no more questions. We'll close the session. Before that, I would like to thank Dr. Rajkumar Ramamurthy for his very nice presentation and interesting topic. Thank you, Dr. Rajkumar. We hope to continue the same from you. Yeah. On behalf of the PG students, staff, and Principal in charge, Professor S. Marimathu, and on my personal behalf, I would like to extend my heartfelt thanks to you, Dr. Raji. Thank you very much for your nice presentation and clarification of doubts. Keep inspiring us, our students. Okay, if at all any doubt, I request the participants, you can directly mail to him. He will be ready to answer your doubts. We'll put his email ID in your box. Okay, there are no questions. Right, we'll close. Before that, I would like to thank. Okay, Raji, please leave the meet. Thank you, Raji.
Thank you very much, sir.
Thank you for your patience, and you readily accepted our request. Keep encouraging us, encouraging our students, inspire our students. Right? We will please.
Thank you very much, sir. Thank you very much for all audience. Yeah. Bye.
Bye. Take care, Raji.
Take care, sir. Take care.
Yeah. Before we close, I request our participants. Now the feedback form is with you. I think probably you'll be receiving this. It will be on for next 10 or 15 minutes only. Kindly fill the details. You will be receiving the e-certificates. It is now in the chat box. So please, thank you very much for joining with us. And the feedback is in description in the YouTube channel. The link is given in the description. You can use that. So thank you very much for the support and your patience. And once again, on behalf of the staff, students, and on my personal behalf, and our principal in charge, Professor S. Marimathu, I would like to extend my thanks to the morning resource person, Dr. Sivasurendra Chandran, and the afternoon resource person, Dr. Rajkumar Ramamurthy, for their concern. And I take this opportunity to thank our RJD who has inaugurated this webinar in the morning and initiated the proceedings of the afternoon, Professor S. Marimathu. Once again, I thank every one of you. We'll meet you soon. We'll be doing this kind of webinars in the days to come. We expect the same cooperation from you. We'll try to continue this kind of seminar in the days to come. Thank you. Thank you very much.